Thank you everyone for attending this talk. Based on the previous talk, I see that there has to be some kind of online streaming. So thank you for whoever is checking this out from the stream. I'm very excited to be here today. And today we're going to talk about open source software security, here be dragons. Who is familiar with this term, here be dragons? Is anyone familiar with this term, here be dragons? Okay, 1, 2, 3. So this term is usually referred to on maps, really, really old maps or maps of fantasy worlds for unexplored areas. Those unexplored areas in these maps, usually there is a picture of a dragon and here be dragons, right? So it's essentially we're referring to unexplored territories. Later, I'm going to come back to this term because I'm going to refer what I'm referring to with here be dragons in regards of open source security. But let's just spend a couple of minutes talking first about software. My opinion, this is my opinion, we are witnessing right now a software revolution. In the sense of companies right now, they are evolving into software companies. So I'm going to give you one very, very good example. Think about a car. A car 20 years ago was probably a driving wheel, an engine, 4 tires, and not much more, right? What is a car right now? Think about maybe, let's pick on a vendor, Tesla. Car right now is a set of computers interacting to each other and giving directions to those tires, the engine to operate, right? So to some degree, these companies that they were not involved in software development, they had to migrate or they had to evolve into software companies just to be competitive, right? Keep that in mind. And of course, open source has won. And I want to be clear on this. Open source has won. There was a couple years ago, there was a study, I don't remember who was the entity doing this study that said that 76% of companies use open source as part of their software development. My take on this one is that 76%, okay, 24%, they still do it, but they don't admit it, right? So open source is key on the development of current software. I wanted to also talk about what we're going to talk today about the agenda. So we're going to present the problems on open source security. We are going to talk a little bit about what my current company, GitHub, is doing for this. We're going to explore the here be dragons territory, which is variant analysis in open source security. We are going to present 3 cases. Who wants to be able, at the end of this talk, to automate finding vulnerabilities in the Linux kernel? That's something interesting, right? So I see a couple of people that are interested in finding 0 days in Linux kernel. So after this talk, my intention is that you are going to be able to find on scale vulnerabilities in the Linux kernel. And we did it, and we found 3 remote code executions in the Linux kernel through Wi-Fi. So that's my intention at the end of this talk, to have the tools and the processes that we put in place for doing this. But first, let's say who I am. Fermin Serna. I'm a Spaniard. Thank you for the presentation before. I have 2 titles, but just 1 salary. The first one is Chief Security Officer at Semel. The reason for that, I joined Semel 5 months ago. Previously to that, I was head of product security at Google. And I'm also a distinguished engineer at GitHub. The reason for that is because GitHub recently acquired Semel. We'll talk about what Semel is, what are the projects and the products that we had in place. So previously to Semel, 5 months ago, I was head of product security at Google. I was responsible for all the products, and its security, proactive security, reactive security, and a lot of engineering efforts in between. All Google products except of Android and Chrome. The reason for that is because they have their own security teams. Before that, I've always been involved in exploitation, software exploitation. If I recall correctly, my first exploit was in 1997. It was an LSOF vulnerability that I successfully exploited. No software mitigations or nothing like that. And I've always been linked into this. I really, really enjoy being challenged by all these mitigations that they are in place and be able to overcome them. Other things that happened, I was the initial visionary and developer of EMET. The EMET is a tooling that when I was working at Microsoft in my first time over there, we developed this tooling for enabling mitigations to make software exploitation harder. And as a live fact, I once owned Charlie Miller's iPhone at Pwn2Own. He won, but I had an exploit for this. So let's talk a little bit about the problem. The open source has won, but what about its security, right? So as I mentioned, there was this study a couple of years ago that said 76% of software uses open source. I think that study is incorrect. It essentially is telling that 24% of software is still using open source, but it's not admitting that they are using this, right? So open source has won. It's here to stay. Proof of this is the biggest contributors to GitHub, and I think this is something like 2017. They are Google organization and Microsoft organization, right? So if we were looking into this data 10 years ago, Microsoft clearly was not probably going to be there. Google, maybe they were getting there, but it was essentially maintainers and not companies being there. So open source has won. It's going to stay here, but comes with a lot of challenges around security, because companies, whenever they develop their software, and by the way, their software is usually a thin layer of integration between open source components. Whenever they develop this thin layer of integration, implementing this functionality, they usually have engineers in their payroll for doing secure software development. They maybe have code reviewers from other peers. They maybe implement fuzzing, static code analysis, all these things, right? But whenever you import those third-party libraries, you don't know where they come from. You don't know the quality. You don't know if someone finds a vulnerability, if it's going to be correctly tagged with a CVE. You don't know much about the processes that the maintainers put in place to meet a decent security bar. You don't know anything about that, but you consume it. And let me tell you something. Most of the code, the code that you run on production, I would say probably 80% of it on average is going to be code that you didn't even develop. Think about this. The software that you develop is usually a thin layer of interconnecting other people's code, and you interconnecting it for a purpose of implementing a functionality. So even from a security perspective, this is you need to think into business continuity. You are depending on open source, right? So let's talk about CVE systems. CVEs work extremely well in closed source software. And CVEs is essentially an identifier that you tag into vulnerabilities. Not only the identifier, you also have the metadata explaining which software it is, what type of vulnerability, which versions, etc., etc., etc. It works extremely well on closed source software for the reason that the customers expect the company to fill the metadata for the CVE. But unfortunately, it doesn't work that well on open source software. Question to the room, how many vulnerabilities FFmpeg, I think, yeah, FFmpeg had last year? FFmpeg, this video library to encode the code, so it's parsing a ton of formats, so it's probably going to be prone to a good amount of vulnerabilities. How many? More than 20? Yes? More than 20? More than 50? Okay, no? More than 30? Yeah? Okay, let me give you the answer. 9. How many 2018? Let me give you the answer. 20. So in between this year and last year, there were no more than 30 vulnerabilities in FFmpeg. Gut feeling, is this correct? Or maybe someone missed not to file CVEs for FFmpeg. I'm going to give you the answer. Someone missed and they didn't fill CVEs for FFmpeg. The reason for this is that there is no customer behind demanding this. But the problem, again, is that everyone depends on open source. Nobody controls it. No CVEs. You don't know that vulnerability you're subject to. Yeah. In the same fashion, you don't control the quality. You don't control if someone is trying to embed a backdoor in your system. So this is an example of 2003. It's a Linux kernel backdoor. Can anyone spot the backdoor here? You? Okay, so I'm going to, at least one, I'm going to explain where the backdoor is. Essentially, it's here. Anyone executing these 2 lines of code essentially is going to give the current process root privileges. This is an assignment. This is not a equals comparison. Okay. So again, someone was able to integrate this piece of code into the Linux kernel and think about all the places where the Linux kernel is running. Other problems with open source: supply chain. Obviously, if you are depending on package managers such as npm, pip for Python, there's tons of them. And if someone compromises that package manager, we're in big trouble, right? And someone did it a couple of times. The first one is npm. There was even an npm worm. If you compromise a developer, that developer can embed backdoors in their software, in their own packages, distribute them automatically, and everyone depending on those packages as part of your company software is going to embed those backdoors, right? So, but let me tell you even more. Whenever you start developing a project, you usually say, hey, maybe let's put an example, a Python project that consumes some pip. Pip is the Python package manager, crypto package. So maybe you're saying, yeah, I'm going to use the PyCrypto or whatever the name it is. That PyCrypto package is going to also import other things that you don't even know, but they are going to be there. And those other things, they are going to import other things. So at the end of the day, just by importing PyCrypto, you probably end up importing 100 packages. Do you know if any of those contain a CVE? Maybe yes. So maybe there's at the end of the graph, you're importing, I don't know, an HTML parser, who knows for what, that contains a CVE, a vulnerability. You, by importing a PyCrypto, you're subject to that vulnerability and that functionality. So those are big problems, right? So open source software, it is free, but it is not really free. It comes with security challenges, right? It comes with, you need to invest a little bit into mitigate these risks, okay? So let's talk about what GitHub is doing. So GitHub, my current company, just because of the acquisition, Semel was acquired by GitHub. They essentially see the software development in terms of actors. And there's in this slide there's 3 actors, but there are actually 4. So the first one is the security researchers. These are the people that they identify the vulnerabilities and they disclose the vulnerabilities to maintainers and developers. When we talk in terms of maintainers, these are, we refer them to open source maintainers, package maintainers, right? So in this case, it will be PyCrypto, right? They are the ones they are the internet heroes, right? Sometimes they develop some kind of software and people start depending on them, and by essentially success, they are internet heroes. And then we have the developers who essentially are developing this thin layer of software that consumes all this open source and they implement the final functionality for the product, right? So GitHub is helping on different aspects. For example, and by the way, there is also the 4th actor, which is a security team that orchestrates all this. So GitHub is helping in different ways to all these different actors. The first one, for security researchers, one thing that we're going to start talking now in this presentation is SEMLQL. SEMLQL is going to essentially scale security research. Excuse me for my voice. Then we have the maintainers, and GitHub has been tremendously investing in maintainers so they can do what they are best at, which is developing software, and they can get the help as needed for other security tasks, such as dependency management, see if they were subject of a CVE and all these things, right? They get alerts, they are essentially, GitHub is making their life as easy as possible. And also, finally, we have the developers, which essentially is they are consuming the open source and they are leveraging all the work that GitHub is doing for other team maintainers. So we are assuming that the maintainers are in good shape, and the developers, by consuming those packages, they are getting that security indirectly. But they also have automatic security fixes, token scanning, and all those things, right? So this is not new. This is something that GitHub has been doing for a while. The new thing, and because the acquisition of Semel, is QL. QL essentially is an automatic, we want to automate variant analysis. The idea here is that we treat code as data. We essentially grab your code, we compile it, we generate a snapshot. Think about it as a database. And then we can write queries and query that snapshot. We can say, for example, in this case, this is a query looking for an integral overflow check that is invalid. We can go later into explaining all this. How is this useful for security researchers? So if we didn't have this type of technology where we have a snapshot, the code as data, and the functionality to query that data, essentially you are with grepping millions of lines of code looking for patterns, right? But that is not enough. I mean, 20 years ago, we were grepping for sprintf, string copy, things like that. But now we want to know if this data is coming from here to this other risky place and it's not being validated by doing this, this, and this. You cannot grep for that, right? So with SEMLQL, we can provide this functionality. And by the way, SEMLQL is a product that you can try right now for free. You can go to lgtm.com and use it on open source. There is even a query browser that you can essentially grab this query, put it over there, and query any open source package in GitHub. So again, we treat code as data, and we have the functionality to query. This scales to millions and millions of lines of code. But what is GitHub also doing? And this is something that we started doing in SEML, which is essentially variant analysis. And we do the CV triage. And now it's going to be the deep technical part of this, talk. My team, the security research team, essentially goes through all the CVs that happened during that week, which essentially is 300 to 400 per week. And we discard, obviously, the ones that they are closed source, because we don't have the source to apply QL for this. And we do variant analysis. Variant analysis in the sense of, okay, we understand that there is this vulnerability that we can describe this way, that there was an array reference and we didn't check the offset, things like that. If we can describe it, we can write a query. And we're going to write queries and find the rest. So maybe they found one or two. What about if we could write a query and scan millions of lines of code, or even across GitHub? So this is what we call variant analysis. Find those other things that the original security researcher didn't find. So let's start with a simple one. This is a Linux kernel buffer overflow. So we were doing the CV weekly triage, again, 300, 400 per week. And Nico Weissman, one of my peers at SEML, he found a pattern of an array assignment inside a loop, and during that week there were a couple of examples like that. So she said, okay, maybe we could find interesting things like this in the Linux kernel. So he codified that pattern that he saw through the CV triage into a SEMLQL query, and he ran it against the Linux kernel. Obviously, he found something like 1,200 places. So we are scaling from millions and millions of lines of code from the Linux kernel to 1,200 cases. So there still is something that you need to go and spend some time on this. So what we did is we went to Twitter and we said, okay, you know what? I mean, we found all these places that there were very suspicious. So our friend Tavis Ormandy from Google Project Zero, he said, okay, I'm going to give it a try. I'm going to go through these results and see if there is something. So very quickly, he found a couple of interesting places, and there were real vulnerabilities over there. And Linus Torvalds, a couple of days later, he fixed them. So let's go deep into the details. So as you can see, we were looking for this condition. Well, on a loop, a while condition, or a for loop, we were looking for an array where we're assigning a value to based on an offset. And we wrote this query. I'm not sure if the query can be seen correctly, but essentially, here's the interesting part is like, if there is an assignment, first of all, here, assignment A, if there is an assignment that is within a loop, and there is and that assignment, the left value is an array, and the indexing part of that array is I mean, essentially it's a write access to the array, right? And if it's inside the value, if it's inside the loop. So again, this is not something that you can grep. this is not something that you can manually go looking for patterns in source code. And the Linux kernels is millions and millions of lines of code. By running this query, essentially we went from potentially weeks of going through lines of code to running this. I think it was less than probably 2 or 3 minutes of running this query. So what happened is what I said is like Nico, he wrote this research query. Research queries are not highly precise. It's essentially reducing the problem of looking into millions of lines of code and it's reducing into looking into potentially tens or hundreds of places, right? So he said, okay, we did this. We found a lot of potential issues, but I don't have the time to go through these 1,200 call sites. Can we crowdsource this? Can anyone help? And Tavis, he said, yeah. And by the way, I found one and Linux fixed it. So this is a perfect example of what I meant about. And by the way, this is the source code for the vulnerability. The vulnerability is quite funny. Is whenever you plug a monitor, an external predictor, in this very similar way that I'm doing right now, there is a protocol where the monitor or the projector talks to your computer, and that protocol is implemented in the Linux kernel with this code. And there was a vulnerability because essentially there was this SVDN variable that is never checked if it's bigger or not than the array length, right? So this is a perfect example of, we went through the CB cases, the CB triage, 300, 400, again, 300 or 400 per week. Think about the amount of work that is going through 300 cases, understanding vulnerabilities, etc. We found a pattern and we ran it on a Linux kernel finding vulnerabilities. The type of query that Nico wrote is what we call a research query. A research query is not a highly precise query. It's going to give you false positives, which is okay. Still, we're scaling down from millions of lines of code to tens or hundreds of places. There are other type of queries that they are the highly precise queries, what we call the out-of-the-box queries, which, by the way, are in open source. Anyone can look at them, and you can run them on open source in lgtm.com. You can find them in github.com, semlql. You can find, I think there's 2,000 queries those are highly precise and what we call out-of-the-box queries. But here we're talking about research queries. There could be false positives, and that is expected. We're essentially reducing the problem. So the next case that we're going to talk is about U-boot, and this is more like a journey about how we did the research and how we use QL to find vulnerabilities in U-boot. The previous one was vulnerabilities were found by Nico Weissman, my peer. These ones were found by me. So let's talk about U-boot. U-boot is an open source bootloader. There was a talk before in Ballroom A where they were talking about some operating system and they were using U-boot. So essentially, it's open source bootloader used in a lot of places. If you go to the Wikipedia page, it's being used on the Kindle Fire, at least in the past. I'm not sure now. Chrome OS devices, ARM devices, and mainly IoT devices. So if you have at your house a Nest device or, well, not a Nest device, if you have at your house a thermostat or some IoT devices, most likely it's using U-boot. Couple of things that I wanted to mention: supports verifiable boot. So verifiable boot prevents someone to boot a kernel that is untrusted. So any vulnerability before the verification happens essentially means that there's a jailbreak. So by definition, the partitions of the device, SD cards or things like that, they should be treated as untrusted. So parsing the Linux kernel from partitions and all those things essentially is parsing data. There could be vulnerabilities over there. So if you find a vulnerability over there, it's totally fair, and it could be a jailbreak. And also networking. And the vulnerabilities that we're going to disclose today, well, they were disclosed, but the vulnerabilities that we're going to talk about today, they are in the NFS TCP/IP stack. So first, what we need is seed vulnerabilities, right? So when I started looking into this code, the first thing that I did is, okay, let's try to understand how NFS is being used, and let's try to get a sense if this code is has a good sense of security, right? If it was developed with security in mind or not. Clearly, I mean, it took us probably less than 5 minutes to realize it's not the case. There are clear examples of insecure code practices, right? In this case, we found 2 mem copies that they were being used with. There's a third parameter that is the size of the main copy, and it was coming from the NFS packet, right? So the NFS data essentially is coming from the network. It's totally untrusted, and they were grabbing some data over there and they were feeding it to us the third parameter of main copy as the size, right? There were no size checks, and essentially the vulnerabilities are here. So rlen is the variable, essentially is the result of a function or a macro, depending on the operating system and the libc and all those things, called N2HL, which essentially converts a number from network to host, right? There is then rlen is being used in 2 places for memcopy. So here we can see the vulnerability counter in the top right goes +2. So then we have the 2 seed vulnerabilities, and we are going to apply QL to find more, right? As I mentioned, I don't want to spend more time going through the code, looking for similar issues. If I had a tool to do this, to automate this, it would be amazing, and we had it. So what we did is we started looking around, and this is kind of the journey, the research journey that we put in place, right? So the first thing that we want to do is we want to find all the colors for memcopy. This is the second query. And essentially, this is the first query. And in U-boot, apparently there's 191 instances of memcopy. 191 places where memcopy is being called, right? We don't know if the third parameter, the size, is coming from the network. We don't know if it's coming from this partition. We don't know if it's coming from a trusted place. We don't know, right? So we just know that there's 191 places where this is happening, okay? Then the second query is essentially we want to understand the places where data coming from the NFS packet, the network, untrusted data again, is being used, right? So in this second query, we are checking if there is a field access. So think about a variable dot, in this case, reply.x. We are checking for accesses to fields with the name reply. The reason for that is because if we go back to the previous slide, you will see on the first highlighted part that the packet is rpc packet.u.reply.data, right? So we're using the reply name as an indicator that this is coming from the data, from the NFS data. Which then is untrusted data coming from the network, right? So we found 596 places where data from the NFS packet it was being used, right? So still, we went from probably thousands of lines of code of U-boot to 596 places where data from the NFS packet is being used, and 191 places for that memcopy is being used, right? Still, it is great. We reduced the scope of things that we need to look into, but it's still something that I don't want to spend a couple of days, right? I mean, have better things to do. So we can further refine this query, but given the problem that we're going to solve right now is like, given a problem-specific set of sources and sinks. Sources is the NFS data coming from the network, and the sinks is memcopy. Is there a data flow that links to these two things, right? That's the problem that we're trying to figure out, if there is instances of this data link, right? So we wrote this query. Again, this is a QL query that is a data flow QL query. And if you see here, essentially we have the source. We override the isSource function, saying, okay, we want the sources to be field accesses to reply. So essentially, the source has to be something coming from the NFS. And the sync is the second argument, third argument, but because it starts with 0, of a main copy, right? And we want to find all the places that has this flow, right? Ends up in memcopy as the third argument, and is coming from the network, from the NFS packet. So first of all, we need to validate that we find the previous two vulnerabilities. So if it doesn't find the previous two vulnerabilities, something is wrong with the query, because we're doing variant analysis on seed vulnerabilities. So indeed, this query, if you copy paste it into lgtm.com and you query uboot, you will find, maybe not now because maybe it's patched, but at that moment you will find the two original vulnerabilities plus 4 more instances, right? So we went from 191 and 500 something to check these other 4 places. So let's go through those 4 places. Again, I mean, I think you guys are getting, you folks are getting the idea of, I don't want to spend my time, I would rather spend my time with my daughters. I don't want to go through 500 places and 191 and try to link them. We are trying to refine the query to get a smaller set of results that I can go by hand and check them, all of them. So we started looking into these 4 places. The first one is this case where here there is an if check, right? So we grab the length with this function in 2HL. We grabbed something from the NFS packet, RPC packet.u.reply.data. As we mentioned, this is the data that is coming from the NFS socket. And unfortunately, there is a check here. If this length is bigger than a macro, we constrain that length to be that macro, right? And then we copy into some variable, and this variable, by the way, has a size, is a buffer with the size NFS3_FH size. We copy something into that, right? So we found this instance was essentially data comes from the NFS packet going to memcopy with this if check, right? So, but the problem is that the file FH3 is a signed integer. It's not unsigned. So it could contain a negative number. And then that negative number would bypass the check and would essentially would have a uncontrolled memcopy with a huge size. Still, it's a valid vulnerability. So we increment the vulnerability counter with 1. Let's go through other places where this query gave us results. So here's the same story. We have rlen. That is essentially is the result of N2HL that is given as a first parameter data coming from the network. Twice in 2 places, and it's being fed to a function called store block. I didn't put the source code of a store block, but the store block is using this length and is memcopying twice, right? So again, the vulnerability counter goes 2 more, and the other two instances of the query, they were false positives because they were checks in before. And I want you to understand that this query was a research query. It's not an out of the box highly precise query. This is a research query where false positives are okay. I was okay going through 2 cases where they didn't lead to vulnerabilities, but I was not okay to read all the U-boot source code, thousands and thousands of lines of code, or going through those 191 memcopy and those 500 NFS data accesses, right? So this was a research query that gave us 2 additional call sites with, if I recall correctly, 3 additional vulnerabilities. So we had the 2 original seed vulnerabilities plus 3 more and 2 false positives in the query. But then we started thinking, why don't we think bigger, right? We are constraining ourselves too much onto NFS. There is something common in all these vulnerabilities. It's like, it is not only using data from the NFS packet, but it is always using N2HL. N2HL is essentially this function that converts numbers from the network to the host. The host could be big endian or little endian. It doesn't matter. The function is going to take that into consideration and is going to convert them accordingly. So what we did is that essentially we changed the sources. We didn't change the sink. The sink is still, well, it's not here, but the sink is still memcopy, the second parameter. But the sources is we said, okay, instead of being constrained to the NFS data, we want anything that comes from N2HL. N2HL essentially is going to tell us that there's something coming from the network, regardless if it's NFS or not. So we ran this query, and we found 8 new instances. It still finds all the previous ones, which is a good validation that this is still a good query, right? So let's go through the vulnerabilities that we found, right? So again, we're trying to think bigger. Don't focus too much on NFS. Maybe there's going to be other protocols, TFTP, things like that, DHCP, something like that, or maybe even the TCP/IP stack. So that's what we found. We found in the TCP/IP stack a couple of vulnerabilities. In this case, there were integral underflows here and here. There was never a check into this field, IP UDP len. There was no check that it was at least bigger than the header size, the UDP header size. So there was a potential integral underflow. This function NC input packet on that specific argument, that parameter, then later is being used with a memcopy. That's why our query flagged this issue, because it was an N2HL as a source, memcopy inside a sink inside this function, right? So 2 integral underflows leading to massive memcopy memory corruption. So 2 more vulnerabilities. Right now we have 7. So then we went through all the other vulnerability, all the other call sites or instances that the query gave us to look into. Those ones were, I don't want to call them false positives, because they are not false positives. They were essentially checks that we could further refine the query to say, hey, in between this data flow from source to sink, is there any if check that does this, this, and this? We didn't do it because the number of instances, it was not that high. So then we started looking around for other type of vulnerabilities. And this one was quite easy, right? All the helper functions for NFS, they contain the first 5 lines of code and memory corruption. They were essentially copying into a static local buffer, stack buffer, the network packet, and the len. The len essentially is the size of the network packet. So if the network packet was bigger than the stack variable, there was a plain stack-based buffer overflow. And this happened 5 times. So now we went from 7 vulnerabilities to 12. And a very, very similar one, but in this case, if you take a look here, they are trying to prevent the memory corruption. This is the only instance that they try to prevent the memory corruption. They say, okay, we'll copy the packet, but we'll not trust the len. We're going to copy the size of this stack variable. The problem here is that you could end up copying more data than the ones that they are coming from the network. So you could be copying uninitialized data or out of bounds data. Right. So another vulnerability, this makes 13 vulnerabilities. All these vulnerabilities were reported, I think it was May, and they were fixed in August. There are multiple forks of U-boot. I assume that at some moment, all of them, they are going to be patched. And this software is heavily used in IoT devices. So there's going to be a little bit of a nightmare to not only patch those forks from different companies, but to get these patches to these IoT devices. That's the bad news. The good news is that NFS is not usually very much used in IoT in your house, right? It could be used while you're developing, while you're a developer and you are in your company developing the latest framework for this IoT. Those are the instances, those are the scenarios that this could be exploited. And to be honest, when we were giving a very, very similar talk in Black Hat, Las Vegas this year, there were a couple of people that they told me, hey, thank you for doing this, because we exactly use this scenario with NFS while we develop, and we could be, our developers, they could be trying to exploit each other, right? So not a real case scenario for someone in their house, but a real case scenario on someone on a company developing IoT devices and such. So we found 13 vulnerabilities. These are the CVs. We have this internal joke at SEML that U-Boot is the Costco of CVs. I'm not sure if people here are familiar with Costco. Are anyone familiar with Costco? You know what Costco is? You know what Costco is, right? So Costco is this place where you go to buy some, some food or some toilet paper, and you end up with a 2-year supply of something else, right? So we went to find a couple of vulnerabilities. We found 13, right? So, and I'm pretty sure that you would probably, we could find more in other scenarios, such as parsing file systems and things like that. So the last demo, the last part is Wi-Fi drivers and trusting lengths. So, but before that, well, actually, this is the timeline. The credit here goes again to Nico Weisman, similar to the first Linux kernel vulnerability. What happened is that there was a security researcher that on August 28th, he or she, I don't know the gender, so he or she found a remote code exploitable vulnerability in the Linux kernel in a driver where they were trusting a length and they were copying based on that length, right? So, as I mentioned, the SEML security research team, now the GitHub security research team, goes through all the CVs. We identified this one, and we thought, okay, maybe we can write a query and run it through the Linux kernel and check if there's any other vulnerabilities, right? And that's what Nico did. And Nico found a couple vulnerabilities. They were fixed, and twice by the Linux kernel. So let's go a little bit into a crash course on Wi-Fi framing. So whenever there is whenever you are connecting, I don't know, your phone with an access point or whatever, there is you send TCP/IP packets that essentially encapsulate TCP, UDP, ICMP, or whatever that encapsulates data, right? But there is an encapsulation on top of that to send those packets between the Wi-Fi devices, right? So this is a crash course on this. The part that I want to mention a little bit is there is this field called IE, and this field is essentially, there is something called EID, which is 1 byte. There is another byte that is the length, and then there is data. That data is supposed to have the length described here, right? So maybe you are anticipating what we're trying to do. The vulnerability is that it was trusting this length, and maybe this length could go up to 255 bytes, and later things could go wrong, right? So crash course, remember this length. We're going to see it in the next slides. And again, this is coming from the network. This is coming from how Wi-Fi devices talk to each other, right? So this is the vulnerability that was found by Huang Wen. So he or she, essentially, they if we go back to the previous slide, this structure we're going to call EID. They grab this structure from with this function CFG 802.11 underscore find underscore IE, and they put it in this this variable, and this variable has the length, has essentially everything, right? And they were essentially memcopying into a buffer from here, and they were using in the size rate len. So they were using this, and this could go up to 255 bytes, right? So what could happen if this buffer is less than 255 bytes? There's going to be a memory corruption, okay? So that was the original vulnerability. It was remotely exploitable, memory corruption. I'm not sure if it was, I'm pretty sure that this was a heap-based, in this case, pool-based, because it's a Linux kernel, memory corruption, remotely exploitable just by sending one Wi-Fi frame, right? So we went back to, hey, maybe, I mean, this is easily codifiable. This is essentially data flow problem. If something coming from here, if it ends up in memcopy, right? So that's what we did. We started with this function, the CFG 802.11 find IE, and anything that goes from there is going to be untrusted, and we wanted to understand if it's going to end up in the data flow as a length, as a size for a memcopy, right? So we and this is the query. The query essentially is anything that comes from this function and ending up in memcopy, right? So we ran this query. We found the original vulnerability. Again, this is a great way to validate if your query is working or not. And we found 13 potential issues. Again, I'm going to repeat, this is a research query. This is not a highly precise query, but we're going from millions of lines of code in the Linux kernel to 13 places. So we went through all these 13 places and we didn't find any vulnerabilities because there were validations of this length, okay? But this was in one driver. What about the other drivers? The other drivers that could be using other helper functions. So it could be something that is not this function, something that is custom made. We want to check for that. So I want you guys to check the query because there is going to be a very, very similar slide next, and I want you to understand what is changing on the query, okay? So I'm going to go back and forth a couple of times. You see? Going back, you see? What is changing on the query? Yeah, it's changing the function name, right? It's changing the source, right? So other drivers in the Linux kernel, Wi-Fi drivers, they are using this function to get the IE. And the IE is going to be a field extractor with the first byte, the length, and the data variable length, right? And we are going to use the same sink. The same sink is the main copy, the third parameter, which is the size, right? And here we found 10 instances. Most of them, they had checks, but we found two cases that they didn't have this check, right? So the first one is in the CW 1200 driver, which essentially they were using this function. It was getting the length is in the second byte because this is indexed from 0, and it was being assigned to join.ssid lem, and later it was being used with memcopy. Again, this length could be up to 255 bytes. What about if join.ssid is a buffer that cannot hold up to 255 bytes? And that was the case. It was a static buffer, less than that, and essentially it was a memory corruption, again, remotely through just a Wi-Fi beacon frame. So this was the first one, but we also found another driver, CFG 811, which had this very, very similar thing, right? So they were using this other function that we identified to grabbing that structure from the Wi-Fi packet, and the length in the byte number 2, in this case 1 because it's indexed by 0, starting in 0. They were assigning to data the reference length, and that data the reference length, it was being used in memcopy. What about, again, if SSID is a buffer? I don't care if it's stack buffer or static buffer or heap allocated buffer. If it cannot hold up to 255 bytes, there's going to be a memory corruption. So that was the second instance of this vulnerability. We started with the original vulnerability that was using a helper function to grab that data from the Wi-Fi. We did a query. We didn't find anything else. Still very useful to have a query that tells you that there is nothing else, right? I mean, that's the information. Before we wrote the query, we didn't know there was something else or not. So based on the original query, there was nothing else. Then we wrote another query based on a little bit of code review that we did on other drivers that they were using this other function, and we found 2 new vulnerabilities, remote code vulnerabilities, just by sending one beacon, right? So I guess that now you see the power of, you do a little bit of variant analysis, you find a vulnerability, you understand it, you codify it, and we go from millions and millions of lines of code, I'm not sure if it's millions or hundreds of thousands, the Linux kernel, to running a query easily, couple minutes, maybe 10 minutes because of the size of the Linux kernel, and going from that size, that type of code and its size to just review these other 10 places. Some of those 10 places is going to be false positives or there's going to be checks, but you end up finding vulnerabilities. And in this case, a remote code execution in the Linux kernel, even before anything. This is it comes from the network, and this is the first piece of software that touches this data. So this is even before any TCP/IP stack, right? So I hope you see the value of QL that scales security research, right? Instead of grepping and spending hours and weeks, you use this, you codify it, you run the query, you go through them, and you find vulnerabilities. So as a recap, we talk about open source. We talk about there's a software revolution that companies are essentially evolving into software companies. We talk about the reliance on open source software. We talk about open source software. Although it is free, it is not really free from a security perspective. It comes with a lot of problems. We talk about those problems: CVE, supply chain, code quality, and we also talk about what GitHub is doing, trying to help all those actors. We talk about QL. QL is a SAML technology, which, by the way, is free for open source. You can go to lgtm.com and right now run these queries against the Linux kernel. And we talk about 3 cases. The first one was the plugging untrusted monitors. In my case, I'm a little bit foolish today to trust you guys. There could be vulnerabilities over there. And with the help of our friend Tavis Ormandy and Linus Torvalds, there is one less vulnerability in the Linux kernel. We talk about U-boot journey, a research journey, how to go from small queries, get the memcopy call sites, get the NFAs, link everything together, and do the triage, find 13 vulnerabilities, the COSCOF vulnerabilities. And then we did the Linux kernel Wi-Fi drivers, where someone, he or she found an original vulnerability. We understood it. We codified into a QL query. We didn't find anything initially, but we refined the query with other helper functions, and we found 2 extra remote code execution vulnerabilities in the Linux kernel, right? So I hope this demonstrates the powerful, how powerful QL is. And yeah, I think we have a good amount of questions, so we're going to go for them. Thank you.
Are there any questions in the audience? Then we go straight to the Slido questions. The first question: do you think the results from SAML QL are different than Zscaler? If yes, where the difference would be? If no, how would SAML QL be reaching same logical condition differently than Zscaler?
So I understand where they are going with this question, but they are 2 fundamental different technologies. So the goal for those 2 functions is the same: finding vulnerabilities. But Zscaler is more like a fuzzer, essentially brute forcing and sending bogus data to interfaces that they know about to see if it crashes or not. QL is more like a variant analysis automation tool that, based on an initial vulnerability, we codified and we found other things, right? So we're trying to do the same thing, find more vulnerabilities, but by implementing through different techniques. The Zscaler is more like brute forcing, fuzzing. SAML QL is more like codifying a seed vulnerability and trying to find similar issues.
Okay, that was our top question. So the gentleman or lady can collect their prize after this.
That was probably my wife.
The second question: do you... Sorry? Oh, I thought somebody said something. With the amazing movement of open source, what do you see as the next step or leap over the next 3 to 5 years?
So open source has won. Open source is here to stay. And we need to help maintainers. We need to help developers. They need to be focusing on what they are best at. They need to be developing. They should inherit security. And I'm going to be very, very clear about this. And this is more or less my new job at GitHub. We need to democratize security. We need to make security easy for everyone, including developers. They don't need to know about security. They should inherit, they should leverage security. They should just say, I really want fuzzing. I don't care about how it happens. I enable fuzzing and I get results and I fix them. They don't need to know the inner details of code coverage, breaking plateaus. I mean, fuzzing is one example, but it applies to everything. So what's going to be next is, in terms of security, we need to raise the bar clearly because of the dependence on open source. And we need to make it easy for non-security folks to adopt, to inherit, to leverage security in an easy way. In short, democratizing security.
Clear, very clear. The next question, do you think copy-pasta code, especially in open source projects, are becoming very common? We've been facing a lot of generic risks when developers go on stack change, etc., and get code and use it.
Yeah, in fact, if you go to a couple of packages, and I'm going to pick one, LibreOffice, they bundle, they grab libraries like libpng on probably $100, and they bundle them inside their source repositories. Then, regardless of what happened in the upstream repository for libpng new vulnerabilities, unless LibreOffice keeps the pace of patching things, they are still going to be vulnerable. So that's more on grabbing a package and bundling into your software. If we're talking about copying software, copying functions, copying big chunks of source code, not just a full package, I think SEMLQL has a tremendous opportunity to, once you know about vulnerability, actually, let me think bigger. Each major CVE should have a QL query attached that later you can go to lgtm.com or where you can run it across GitHub. And regardless if it's copied or not, you're going to find all the instances where this vulnerability exists, right? So code cloning, copying is a problem, but SEMLQL can help you to find problems even on those scenarios.
What about design logic vulnerabilities in open source software?
So, great question. And the answer for this is that SEMLQL is not only, I mean, we had cases here that we were finding memory corruption vulnerabilities, but SEMLQL is also very useful to find logical issues. And I'm going to give you a couple of examples. Apache struts, the way that famously Equifax got hacked. We did variant analysis on the Apache struts, and Apache struts is Java, right? So there is no memory corruptions. We did a variant analysis on Apache struts, and we found 5 more extra vulnerabilities 2 years ago. Those are logical issues. Those are essentially data coming from the HTTP request and being deserialized or being used as OGNL. Those are logical issues, and we found those. So SEMLQL not only finds memory corruptions, in this case we only put examples of memory corruptions, but it also finds design vulnerabilities. I'm going to give you another example, SIP-slip. SIP-slip is this vulnerability type that essentially you're trusting data paths from zip files, untrusted zip files, and you're using later them for opening, reading, writing, and this untrusted data paths could contain directory traversals, .wac, whatever, right? So QL, we have queries for SIP-slip, so SEMLQL can find those logical vulnerabilities too.
What language are supported? Is it possible to add any languages?
So this is an amazing question. So right now it supports C, C++, C#, Java, Python, Go was just released. One of the things that we want to do is to provide anyone with the capability to add new languages. We want to open source kind of an API that if you an API so you can create your own snapshots based on that new language, and then you can apply the queries to that new snapshot. So I'm going to give you a couple of examples that people have been asking us. The first one is other languages such as PHP or Ruby. We want you to have the opportunity to implement it yourself. If you don't do it, and if there is a lot of requests, maybe we will do it ourselves. But we want this to be a community-driven thing, right? And the other example that people were asking us is about binaries. It's like, well, we don't have the source code, but binary, we want to query a binary, right? So maybe you can decompile it and through this binary import that data. And we can build the call graph and things like that, and then you can query a binary. It is not there, but this is the where we're going. We want to have some kind of an API where you can do it yourself, and you don't rely on us, to be honest.
Sounds very promising. Is it possible to run SEMLQL on a local project without internet connection?
So on open source right now, you have to go to lgtm.com. And the reason for this is because we need to set up a little bit of grabbing the snapshots and running the queries and all these things. And this is not as easy as it sounds. I would say that it is possible if you have the tooling for doing this, but on open source, the easiest path is to add your project. If it's in GitHub, it's just a question of adding an app, and you will get you can run queries against your project, your custom queries, or you can run the out-of-the-box queries that they are already open source against your project, not only once, but on each pull request. As you continue to develop, you will get notification about, hey, based on this new code, you introduce this type of vulnerability or not.
You talked about patterns. Is it possible to use machine learning and/or artificial intelligence to detect potential issues?
Is it possible? Yes, and we're hiring. So if that person is looking for a job, great. No, actually, we use machine learning for. There is an interesting problem here where running a query on scale on millions and millions of lines of code on the Linux kernel, it is not as easy as it sounds, right? And there is a machine, and I know for sure that there is some efforts on machine learning to, we run this query on this subset of structures or data, but we don't do it on this because we know that this query is not going to gather results in this area. So there is some research that is being done over there just to make this scalable.
It's really, really impressive. Thank you very much. And please have another round of applause for our speaker.